Hey, welcome back to Fat Mama Physics. In this video, we are going to go over an example on Coulomb's law and the electrostatic force. Here is the question, and let's get started. We have an electron. Let's draw an electron here on this side. Here's a diagram included, but I'm going to draw it again down here so we get a little bit more space. We have an electron here. It is placed 2 times 10 to the power negative 2 meters from a 2.5 microcoulomb charge. Okay, so looks like that first charge there is positive. So here I'm going to put that over there. Okay, this is 2.5 microcoulombs. We can label the distance. This from here to here is 2 times 10 to the power of negative 2 meters. And it is placed also a further distance, 3.5 times 10 to negative 2 meters from a negative charge, which I am going to place over here. Oopsies, that's not positive. Okay, this is negative 2 microcoulombs. Don't forget microcoulombs is 10 to the power negative 6. And this distance here is 3.5 times 10 to the power of negative 2 meters. Okay, and we want to find A, the net electrostatic force acting on the electron, and B, the acceleration that this electron will experience. Hey, the mass of the electron is given to us, and it should also be in your data booklet, so you don't have to memorize that for any reason. But let's start with question A. I'm going to use green for that matter. For question A, we want to find the electrostatic force acting on this electron. We know that negative charges will be positively attracted to positive charges. So actually, I'm going to call this guy A, and I'm going to call this negative charge here B. So it's going to have a force of attraction to A. So I've drawn the Coulomb force towards the positive charge, and it's going to be repelled by this negative charge in the opposite direction, assuming they're all in the same line over there. And this guy, he seems a little bit further away, and he also has a smaller charge compared to the positive charge there. So I'm going to draw this force vector a little bit smaller in comparison to A. So technically there should be vectors up there as well. So when I do add these two together vectorially, then the net direction of my electrostatic force should be towards the right. So to find out this total force, or in other words, finding the net force, I am going to find the net force towards the right. So that means I am going to have to take FA, the magnitude of FA, minus the magnitude of FB to give me the net force towards the right. So any sort of positive and negative charges, I am not going to include them in my equation. So for example, Coulomb's law is K, Q, and Q1, Q2 over their distance between their centers squared. So for the charges that I will put into my Coulomb equation, I will put them as just the positive value, because I've determined the direction of the force already. I don't need to consider the charges again. Okay, I've considered the charges and the attraction and the repulsion in my my diagram. Technically, kind of like a free body diagram, so I don't need to do that again. All right, so now I'm going to calculate this force. So FA is going to be K, which is Coulomb's constant, times Q. I'm going to treat Q as, for A is going to be QA. I'll label that as QA. And then the small q is going to be my electron, which I'm going to use E for, divided by their distance, or this is going to be the distance to to A squared minus the Coulomb force due to, that's going to be B times the electron, the charge on an electron, divided by the distance to there squared. Okay. All right, we know that for an electron, the elementary charge for either proton or electron is going to be the same, and that's going to be 1.60 times 10 to the power negative 19 coulombs. So that's so I will use that as well when I'm doing this question. And K, it is roughly 9 times 10 to the power of 9, according to the according to your data booklet, which then you can take a look. It's right there. 8.99 times 10 to the power of 9. Very close to 9. I usually use 9, but if you want, but probably good idea to use this number for your for say on an IB test. Okay. There's some other numbers here that's going to be useful. Here's your elementary charge for your electron. Electron rest mass, which is in the question, proton rest mass, and neutron rest mass, which you may use as well. So let's go back here. All right. Okay, so really, I'm just going to plug, this is pretty much plugging numbers in at this point. So this is going to be 8.99 times 10 to the power negative 9. I'm not putting any units, unfortunately, so QA, 2.5 times 10 to the power negative 6 coulombs, and the electron, which is 1.6 times 10 to the power negative 19, all over their distance squared. Don't forget that squared. A lot of students will forget that when they plug in their numbers. Okay, minus the other one. Okay, this is just pretty much plug and chug at this point. Oh, sorry, that should be positive 9, not negative 9. My bad. Okay, so this is, again, I am not going to put in that negative sign for the negative charge because I've determined the force, the direction of the force in my diagram already. Okay, that's negative 19. Yeah, my computer is really slow right now, so it's and it's doing all sorts of funny things. Okay, so there it is. Okay, all over 3.5. 3.5 times 10 to the power negative 2. This is in meters. That should be in meters squared. Okay, and this next part here is just putting all this into the calculator. So if you want to spare the boring part, you can skip this over. Yeah, I'm just going to do it on my calculator down here. So saves us a little time. I get 6.64, which I'm going to round to, let's see how many sig figs we have. About 2 sig figs. So 6.6 times 10 to the power of negative 12 newtons. I'm going to store this on my calculator because we're going to need it for the next one. Next question. Okay, the next question is finding the acceleration of this electron. Well, we know that acceleration can be found from the net force, which is Newton's second law. By dividing both sides of the equation by the mass of the electron, I can solve for the acceleration, and I use the net force I got above. Make sure I don't round anything. So I'll use the value on my calculator, and the mass of the electron, it is provided in the question, also in your data booklet, which is right here, 9.11 times 10 to the power negative 31. Very small mass indeed. Kilograms. Okay, so then after we divide the two, we get 7.29, which we're going to round up to 2 sig figs. 7.3 times 10 to the power of 18 Newton per kilogram, or you can use meters per second squared. And don't forget, for both of these questions, we need to specify directions since both numbers here are vectors. So here, since in my original diagram, I'm talking about the electron accelerating, moving towards the right, I'm just going to write towards the right for my direction. Okay, and it's also specified in my diagram above. Okay, so that's going towards the right. Okay, so that's it. All right, box your answers. Here we go. All right, so maybe some key takeaways when you're doing these kind of problems is that for putting in negatives and positives for vectors, draw your free body diagram. When you've determined the direction of your net force, you don't need to put in negative and positives for your charges. it makes it less confusing, and it also gives you a challenges you, or it forces you to think more conceptually as opposed to just number crunching. And the other thing I would say to take away is that even when you're putting things in your calculator or you're showing your steps, having that squared, that squaring that distance on the bottom tends to be left out a lot. So please don't forget those two. And otherwise, hopefully you learned something from this video. Wish you good luck. Fat Mama Physics signing out.